Okay, guys, now we are recording. Okay, welcome to module 5. That's basically the biggest module in this course. It's an important module, and I would say it's very, very simple again. There has many things to cover in this course, in this module, but but they are all simple and straightforward. You will see. So it's about beam. Everything's about beam, bending beam, basically. Let's get started. So what is beam anyway? It's a structure. Of course, we use it in construction, like bridges, buildings, and so on. By definition, we call something like a structure a beam when basically when we say the length compared with the cross section is large. So let's say if I have this beam and maybe this is my cross section, or to be exact, let's show it like that. Or any shape, it doesn't have to be like a rectangular shape. Oh, I don't have room, let me try it again. It can be, the cross section can be a circle or any complicated shape. It can be an I-beam, it can be anything, all right? So these are the cross section. So basically we say it is a beam if the length compared with the cross section is too large. By too large, it means at least we say 20 times bigger, right? If, for example, you have a structure which the length is 100 meters, then 100 meters is too big. Let's say 100 centimeters. Then we say the diameter, if it's circular, or the width of the cross section is around, let's say 1 centimeter or 2 centimeters, right? Then we consider it as a beam. We have different type of beams, which you should know the names. A simple beam is a beam like this one, the first one, which has a joint at one end and a simple roller at the other end. Cantilever beam is very common. It's fixed at one end. Again, this symbol that we use, it means this beam, we fix it inside a wall, and it's fixed there, it's not gonna move. So we call it a cantilever beam. And by the way, cantilever beam is something that you're gonna see a lot in your future courses. And many industrial, let's say in many industrial application, we can simplify things to a cantilever beam and solve a cantilever beam. This one is more like a simple beam, but it has like a side which overhangs basically on one side. This one is more like a cantilever beam, but one end has a support. That's why the name is like that. And this one, which is fixed at two ends, it's called a fixed beam. Okay, it's just simple names. You don't need to memorize them. Just be familiar with them. Like this one, of course, which you've heard it a lot, cantilever beam and simple beam, people may use them in wording, so you should know what they are talking about. Then we use these beams to put loads on them, but there are two types of loads. One is the concentrated loads or point loads, which you are familiar with. This is something that you've seen so far, like this one. You have a load P or a load F or a moment, a torque or moment M. They apply at one point. But in practice, let's say if you put your textbook on a table, right? Can you say the weight is at one point? No, it's distributed over the area of the textbook, right? Or when you're standing somewhere, like for simplicity, we say your weight is coming at 2 points, but in fact, your weight is distributed over the sole of your, let's say, shoes, okay? The area that your shoes or your shoes print on ground. So this is what we call a distributed load, which is basically all the loads in practice outside. They have been distributed over an area. So when we talk about the load being distributed, usually we talk about the intensity of a load, okay? And what is intensity of a load? Let's come back to this beam idea. like here, for example, let's say I have a beam, and over this beam, I have a load which is being distributed. Let's say this beam, this is maybe a snow coming down on this portion of this beam and being uniformly distributed over this beam. Then instead of like a number, we say like here, we say simply this force is 10 Newton. Here we have a number which we call it intensity, which is basically the magnitude of the distributed load. Distributed load, okay? People call it intensity. And how people define this, for example, they say this Q is equal to 100 Newton per meter. It means that every meter there is 100 Newton equally being distributed, okay, for this 1 meter of things. This is the way we say it. Or we may say that this Q is, let's say, 20 pound per inch. Again, it means over 1 inch, I have distributed 20 pound force, all right? The second one is like this one again, it has a name, we call it a uniform distribution, because it has been distributed uniformly. But the other one, you see, the distribution at the beginning is, the intensity is 0, like the second one. But as we go at the end, the intensity is 0 here at the beginning. Intensity is 0. It linearly goes up to get to the intensity, to this maximum intensity, right? So this one is called linear load, or some people call it a triangular shaped load, okay? A common use of this load, or maybe something that we can talk is like this dam. Let's say for a river or for a lake or something, you put a dam. And this is water. I know the water is pinky, but that's not my fault. This is your textbook fault that put this pink water. So we know that there are a formula for pressure. If at the top, we put our axis there and we call this one Y, we know that at the very, very top here, there is no pressure, right? Pressure is 0. But as we go down at the bottom, pressure is maximum, right? Pressure, we have a formula for pressure, which is rho g h, which here I put Y here. And we know as we, like the pressure here is like the maximum. But as we go to the top, the pressure becomes smaller, smaller until it becomes 0. And it linearly increases. So basically then as I go over here, the pressure is smaller, it becomes smaller, smaller, until it gets to 0, right? So that's a sort of an example of a linear distribution load. Okay, let's go back again to what we said here. All right, so how should we deal with then this distributed load? So there are simple way, and is to find their equivalent. That's how we do it. How we find the equivalent, it's 2 simple things that you need to know. For a uniform load, you find the centroid, which it's obvious, it's a rectangular shape and center must be there. By centroid, I mean the center of this load. And the equivalent load simply here is Q multiplied by A. The intensity multiplied by the distance. That's simple. This is all you need to know. So whenever you see a distributed load, a uniform distributed load, just remove it, put one concentrated load, which is the intensity multiplied by the length. You see the intensity has the unit of Newton per meter. Now when you multiply by the length, which is in meter, let's say, you get 1 force, Q multiplied by A, which the unit is Newton. What about a rectangular shape? A rectangular shape, it's first of all the centroid of rectangular shape. If you recall, we touched it a little bit before. We said like the centroid of this guy is in a distance which is A divided by 3. Like this distance is A divided by 3, like in previous lecture. And when you saw a rectangular shape, a right rectangular shape, a triangular shape, then simply replace it with a force which plays at the centroid. And this time be careful, because it has a linear shape, unlike this rectangular shape, this triangle, the equivalent load is Q multiplied by A divided by 2. In other words, we are just calculating the area of this load, right? Here, the area of a triangle is Q multiplied by A divided by 2. Here is just simply Q multiplied by A in a uniform load, okay? For a uniform load, simply the center of this load is like in the middle here. For a triangle, the point that you need to put this equivalent load is A divided by 3 from the one side, right? Be careful from one side, and or from the tip here is 2A over 3. Like from here to there, and again. Like this distance is, it's obvious, it's 2A over 3. All right. So in other words, I divide this side to 3 portions, and I put this load at the portion which is closer to this larger intensity. This is how we deal with the distributed load. So before I solve an example, do you have questions so far? If it still is not clear in example that we're going to solve, you're going to see how we deal with it. Are we good? Okay, let's move on then. So for example, we want to find out the reaction at A and B. So how we deal with this problem. In previous basically chapter, you saw problem of equilibrium, and you know we start with free body diagram. We do the same here. A is AX, AY, and B is a simple support. It has just B, so that part is easy. So we call this one B, this one is AY, and this one is AX. All right. Now, instead of this big, ugly distributed load, I just imagine that it's not there. Instead, I find its equivalent, which is a load over there. And I just need to be careful where to put this load, okay? Let's say the whole area, like the whole length here. No, not that one. Sorry about my drawing a little bit here. Anyway, so the whole thing is 6 1/7 meter, right? Be careful, this distance now is how much? 3.5 meters. All right, do you agree, guys? So don't rush to writing it down. Divide this 6 by 3. You see this load is distributed here, and we have this small distance 1 meter there. So this is where we put the load. So that's the new problem that we need to deal with. Except this guy, what is the equivalent here? 400 multiplied by 7, right? 2,800 Newton. Remember that your unit, be careful about your unit. If the unit of the intensity is meter here, Newton per meter, then the length must be the same, like in meter. Okay, just be careful about that part. The rest is just the previous stuff that you saw in this course. You start with writing your equation. Sum of the force in x equal to 0 give you ax equal to 0. You take a moment about any point that you want. Let's say point A equal to 0, right? So AY is nothing. Then you have this 2800 Newton multiplied by its distance. Be careful again, it's 2.5 meter, right? The distance between the load and here, like this one, I'm just writing it with green so you know what it is. And how it's trying to rotate this beam. So it tried to rotate clockwise, so it's negative. And then I have B multiplied by the distance, which is 10 equal to 0. From here, I will find B. Let's say if I don't make a mistake, if we get rid of that 0 there. Oh, no, it's not that. Anyway, use your calculator and later calculate E. And sum of the forces in Y equal to 0. In Y, what do we have? We have AY, we have 2800, and we have B equal to 0. From here, we can find AY. You see, it's very simple. I just pretended that this distributed load is not there. Instead, there is this pink load, this 2800 Newton load there, all right? And then the rest of solution is just using the equilibrium condition. If you understand this problem, it means you can solve any problem related to distributed load so far. If that's the case, then let's solve this problem together quickly. I want you to think about it for 10 seconds. Always start with free body diagrams. Okay.
Sorry, I have a quick question about the last example.
Okay. Yep.
Would you not split the distributed load into two things, since a bit of it's working in the opposite direction of most of it because of that 1 meter?
That's a good question. So what Thomas is asking, it says that, hey, we have here like these loads over this 1 meter area, and then we have this load, the rest of it over this 6 meter area. So what Thomas is suggesting is, shouldn't we put like one portion like for this small one, and then another one for these 3 meters? You can also do that, but you would get the same result. You can try it later and see if you break it down to 2 portions. One is this portion, right? Hope everybody else can follow. So we have like a portion of load over here, this overhanging, and another portion of the load, like this bigger portion here, right? You can treat these two differently, like finding the equivalent of this small portion here, all right, in the middle, and also find the rest of it somewhere, which is going to be probably around here. That's my guess. And for each one, like for this one, it's going to be how much? It's going to be 400 multiplied by 1, intensity multiplied by length. And this one is going to be how much? 400 multiplied by 6, right? So instead of multiplying the whole things by 7, we break it down to this 6 and to this 1. Now this little guy here, it has the distance of 0.5 meter. Do you agree, Thomas?
Yeah.
And this, the second portion have a distance of from here to here, 3 meters. So in other words, instead of these big 2800 loads, we are using these 2400 plus 400 on different portion. If you try that, you would see you would get the exact same result. Yeah, and I encourage you to try it and you would get the same result, but it just makes your solution longer. So then I suggest whenever you see like a distributed load, more like uniform load distributed like this one here, simply use just one load. Okay? Does that answer your question, Thomas?
Yeah. Yeah. Thank you very much.
All right. So then let's go back to that. Let's clean this up. And not that one, here. Okay. So as I said, we start with free body diagram. So free body diagram, we know that this guy, a fixed beam, has a moment here. And let's call it M0 or whatever, MA, whatever you want to call it. And then we have this AY and AX. Right, so this one is AY and this AX. So a fixed support, 3 unknowns. And then what should we do with this triangle? We get rid of it. How? Simply we say that if I put a load over here, which this distance simply is from here to here, the whole thing is 3 meters. So this distance, 1/3 of that. Oh, I made a mistake. Do you know what is my mistake?
It should be at the higher intensity side.
Exactly, Emily. So that's a good point. Thank you, Emily. So the mistake is, remember always the equivalent load is on the more intense portion, right? Because that makes sense. The center is more closer to the intenser load there. So then it means this distance is 1 meter, or this distance is 2 meters. Okay, be careful about that, not to make the same mistake that I did. So what is the equivalent? We know the area of this rectangle, which is 100 multiplied by 3 divided by 2, gives us 150 Newton. Be careful, this is meter, this is meter. So the rest, you know how to deal with it. Sum of the force in X equal to 0 gives us AX0. Sum of the force in Y equal to 0 gives us AY 150. And taking a moment about this point, A equal to 0 gives us M0 minus 150 multiplied by its distance, which is 6 meters, equal to 0. M0 is going to be minus 900 Newton meter. So if it is minus, it means the reaction at the support is the opposite direction, which makes sense, right? If you try to bend this beam, if you put this load there, the bending must be in the opposite direction. Okay. Any question for this example? Yeah, I guess it looks simple. Yeah, stop me please if I'm going too fast. All right, let's deal with this example. Oh, it looks weird. We haven't seen a shape like that, right?
Actually, I have a quick question, which can apply to both of these.
Okay.
Would we ever find a moment, do any integration, or would we always just find an equivalent point force?
Okay. So Oliver is asking, like in this topic, are we going to do any integration? So his question is related to something like that. Let's say I have a beam more like this shape, and then snow is coming over here, but at the same time it was wind, and then the snow, we are unlucky, hacked on this beam with this weird shape, right? Now, what should we do with this sort of distribution? It's not a rectangular shape. It's not a triangular shape, right? It's a complicated shape. In this scenario, we use integral, right? We do the integral basically, and like we should have the equation for this one. Like here, simply we have a q, but here we have something like qx. Let me turn off this guy. Okay, so, and this is x basically. We do something which integral like that one, qx dx, to find the equivalent, like f. And then we need to do another integral to find where to put this center basically. So that's the way people solve this problem. But in this course, no, you don't need to, because this is a topic coming in future courses like 360. And mainly the reason that I don't teach it in 260 is because you don't really need this one. Because if it's a really complicated shape, then a computer can be used to solve the problem, which at the very end, I will show you how you can use computer to solve all of this stuff that you learn in this course, all right? So then to answer your question, no, we are not gonna in this course to use integral, but to deal with any load that is not a rectangular shape or a triangular shape, we need to integral basically.
Okay, thank you.
No problem. I know you guys are scared of integral for some reason. I don't know why. I remember when I was a student, whenever a teacher write integral on the blackboard or whiteboard, say, ooh, integral. So that topic is complicated. So how should we deal then with this one? Any idea?
We can probably split it
Split it to how?
as a rectangle and a triangle. No?
Okay, that's correct. Yeah, as Mohammed said, in this one, we can break it down to two basically loads. One like basically a rectangular shape and one this triangular shape, all right? Now we have to deal with this like this one. And then we need to deal with the other one, right? So like this, basically rectangle there, and then we simply deal with the other one with the triangle at the top. Okay, so let's say how we can do that. So let's first imagine that this this triangle is not there. We're just seeing this basically this rectangular shape, which is 80 by 3 meters. So we simply know that the equivalent is something in the middle here. And how much it is? 80 multiplied by 3. So it is 80 multiplied by 3, right? And then we have to deal with this rectangle. This rectangle, it's basically, okay, the size, okay, that's one side 3 meter. That's this side, which is 20. So don't confuse again with that 100. So this side is 20 Newton per meter, right? Because already we cut this 80 portion of it, just left with this triangle. So in that sense, the equivalent of this one is gonna be something like that. And I bring it all the way down there because if I put it up there, see, it's just on the air. We don't like that one, right? So, but first, let's say put the equivalent of this guy is going to be 20 multiplied by 3 divided by 2 gives me 30 Newton, all right? And this one gives us how much? This guy gives us 240 Newton. Okay. But we don't want to leave this blue load here up there, so I just bring it down all the way down here. Okay. Yep. That's how we find the equivalent of these loads. And all the distance and stuff, we have them. We don't need to be worried about them, right? Like here, this distance is 1 meter. And this guy here must be 1.5 meter. Right? So that's about it. And I believe the rest you can handle easily. So you start with the free body diagram. A is we have AX, AY, and B is just a roller. We have just simple load B there. B, AX, and AY, which I leave it to you guys to continue the rest. Sigma FX, sum of the force in Y. Remember, sum of the force in Y, you have AY, you have minus 240, you have minus 30, then you have B equal to 0. And take a moment about any point you like, for example, point A or B. If it was me, I took the moment about point B because it's seems less calculation. Let's do it. So take the moment about point B. We have these 30 multiplied by 1, and it is positive. Then we have these 240 multiplied by 1.5. And then we have at the end here is AY multiplied by 8 equal to 0 gives us AY. And here gives us AX equal to 0. All right? So very simple, right? Any question for this one?
It's not. I have a question, but it's not really, I think, related to the topic. But like, if we were to draw the deformation diagram for this beam, just curious, how would it look like with none?
Okay, that's the next topic.
Okay.
Yeah, that's the next one. So Mohammed is asking how we draw the diagram for these bending moment and stuff, which is the next topic. Let me see. Yeah, that's a topic which I can see I don't have time now. Probably you guys are tired. So either I can record this one, because to solve assignment 3, you need this portion. Or what I can do, we can leave this topic for the next week because it's an important topic. And then assignment 3, probably I'll change the due date. But first I need to check to see if you need to know this portion of the module to solve assignment 3. Okay, guys? So I will send you an email or an announcement for assignment 3. Either we postpone it or sort of I check if you don't need to know this portion, then it means you can solve assignment 3. All right? But yeah, we'll continue that one next week. But so far, let's see, is there any question related to distributed load? Again, let's summarize. The concept is very simple. Instead of having a load being concentrated at one single point, we have the load being distributed over an area. But since we are dealing with 2D problems, we're just seeing 2 dimension, like a beam here. Here we say the load being distributed over a length. That's why we see it's like it says, like in this example, 100 Newton per meter. We don't care about the depth. Depths, we assume it's uniformly going there. Like this beam probably has a depth, right? But we are solving it as a 2D problem, and the load is being distributed over a length. When we saw distributed load, simply we find its equivalent, which you saw in this course. We just deal with 2 types of load. One is uniform, a rectangular shape, and then another one is a linear load, which is a triangular shape. Like the most difficult one is going to be something like this one, which you break it down to 2 shapes, as you see it here. And after that, it's just the equilibrium equation, which we deal with. In the next part of the course, we will deal with the internal loads, basically. We want to know what's happening inside. Remember, in this course, we are calculating the stresses, and we said stresses come from the external loads. The external loads result in something inside this beam, and which it result to either bending or shearing, which is the next topic. We leave it for the next week. Okay? Yeah. So before we leave, if there is any question, I can wait and answer your question. If there is not any, we can stop here. Are we good? Okay, if it sounds like that, please just wait for my announcement about assignment 3. And then other than that, I'll see you next Tuesday. And I will send an email to Reza, so he probably is working on your midterm, and he return your feedback soon. And again, as I said in my announcement, I guess yesterday or the day before yesterday, don't worry about your grade. If you made silly mistake and your grade is something that you're not happy, don't worry. I promise if you do better in your final exam, I bring down the weight for your midterm exam lower, sort of you guys get something that you are happy. All right? Okay, have a good day then, if there is no question. Goodbye.
See ya.
See you. See you guys.